All right, let's get started. So today we're going to continue our discussion of security over the network, and we're going to look at another application. If you recall, last time we were looking at HTTPS and this TLS protocol for having secure channels over the network. And today we're going to look at messaging security, which is another important class of applications that you might worry about of their security. And the setup here is that we have some kind of a messaging system running over the internet, and we have users trying to send messages through the network. So Alice might send a message into this amorphous blob of a system, and somehow the message is going to find its way out to another user like Bob, which might be where Alice was trying to send the message. So that's sort of the general setup. We want to provide security in the setting. And as you sort of gather from the paper that you were reading, there are sort of broadly fairly standard things you might care about, like confidentiality. How do we know that no one except for Bob can see our message? There's authenticity, as you might expect, that the right person sent the message. And then there's more sort of elaborate security properties that we'll look at. For example, you might worry about privacy, which is not quite confidentiality, perhaps. You might care about deniability, and so on. So it's a kind of a quite a rich area in terms of different security properties you might be trying to achieve. And one particular reason we're looking at messaging security next is that it's an area that's both important in the real world, real systems, and there's not really an equivalent to TLS. What I mean by this is that in the secure communication world, like TLS is the answer. If you want to communicate to another server, you just use TLS. That's great. You don't need to think too much about it. In the messaging world, there's not really agreement on what the cryptographic construction is that everyone should be using. There's not a TLS for messaging, if you will. Still quite a bit under active development, and every messaging system is slightly different. We'll have a guest lecture in a couple of weeks from one of the lead developers of Zoom's security protocol, and Zoom is developing it again from scratch. Well, they have the foresight for looking at previous designs, but there's quite a bit more in terms of the desired properties in messaging security, quite a bit more in terms of how these cryptographic primitives are put together in every messaging system. So it ends up being quite an active area, and one where you sort of have to understand the cryptographic constructions in a little bit more detail to do the right thing in contrast with TLS. Hopefully it makes some sense as the context for this. And one thing I wanted to maybe start with is contrast all the interesting protocols described in this paper with something like email that you'll use, and just to understand sort of what maybe is holding email back, or why is it difficult to deploy some of these ideas in the paper. So I wanted to sort of give you an overview, if you haven't looked at how email runs. It's some sense of what it might mean for email messages to be sent from one person to another, or send email to some address. There's a lot of entities and steps involved that somewhat contribute to the difficulty of having secure email. So if we might have a user like Alice in our diagram there, if she wants to send a message to Bob or some other email address through email, well, she probably has to run some email client on her PC, and this email client maybe is a web browser if she's using like Gmail, is going to talk to her email server. So maybe this is Gmail. If she's using Gmail, she's going to type in some message into Gmail, hit send. Well, what's going to happen is that Gmail is just going to talk over a protocol called SMTP to a server that is hosting the recipient address. So maybe in this case, Alice maybe sent an email to a mailing list. So mailing lists are somewhat popular. So maybe this is a server hosting this mailing list, and the job of this server is going to be to take the email message and actually broadcast it to all the recipients of the mailing list. So you could have sort of fan out in the middle of your email network. Maybe one of the subscribers happens to be Bob, maybe at IBM.com, just for purposes of one example. So that gets sent through SMTP again to Bob's IBM.com server. Well, maybe Bob decided to forward their email. Like people at MIT forward their email to Gmail all the time. This happens elsewhere too. So maybe Bob's IBM address actually forwards to Bob's MIT address, right? So MIT is going to be yet another server, and this is also going to speak SMTP to send mail to Bob's MIT account, like bob@mit.edu. This, in turn, like another thing that might happen with email is you might have archives. So I think MIT's email system allows you to archive your messages. So maybe Bob configures that, and a copy gets saved. And then maybe Bob's actual message gets sent to CSAIL's mail server. And this is where Bob actually reads his mail. There's many, many hops that are fairly common in email transmission systems. And finally, Bob is using their email client. And the email client is going to speak a protocol like IMAP or POP to actually retrieve the message from Bob's email server. So this is just to give you some maybe point of comparison to what email looks like in contrast to some of these cleaner maybe messaging protocols that the paper talks about. So there's a lot of sort of complexity here, and there's a lot of additional processing. One thing actually turns out to be I forgot to mention, but like a huge thing is spam filtering. So it might be the case that the mail server along the way, like the CSAIL mail server, MIT's mail server, they could all run the messages through some kind of a spam filter to decide, well, is this spam or not? Should I actually even bother giving it to the user? So email is sort of complicated and but super flexible. So I guess if you haven't thought too much about email security before, just to sort of come out and say, people have tried to worry about security in email, but by and large, it hasn't really been anywhere near the kinds of security properties this paper is talking about. One reason why this is the case is that a lot of the email security mechanisms are really retrofit into the email design. So email came first, and then maybe 20 or 30 years later, people decided, well, wouldn't it be nice to add some security properties? And at that point, email was already quite a seriously established enterprise with many systems running. And it's difficult to change a large system, as you've seen in many case studies you've looked at in this class. So that's one reason why email security has been difficult to achieve. The kinds of security mechanisms that have been deployed are really ones that can be done incrementally. So maybe the most, one of the success stories in email security is per hop encryption. So what this means is that various links in this diagram, like this link from Gmail sending mail to this mailing list server, this actually runs over TLS. And so basically the regular SMTP protocol runs over this TLS channel that we talked about before. And this might be also over TLS, but not all of them. So the problem with sort of retrofitting security, like adding TLS support to some world like email, is that you don't really know if the other guy is speaking TLS, or you should expect them to speak TLS. So as a result, a lot of these security mechanisms are really opportunistic. What I mean by opportunistic security mechanisms is that a mail server will try to use a TLS connection to speak to another mail server, but if that doesn't pan out, it'll just fall back to regular SMTP that's not encrypted. And this is easy to deploy and sort of backwards compatible, but means that various active network attackers can downgrade connections to just regular SMTP that's not encrypted anymore. Question? Is there anything in the protocol that might let you say that your message should only be sent over TLS? No, absolutely not. For various, as with any such answers, right? Like the answers wouldn't be very difficult to add this if only you could change every mail server in the world. Indeed, but there's nothing right now, and as far as I know, I don't really know of any even active proposals to do anything along those lines. One sort of reason why that's difficult to do is that actually even this opportunistic encryption over the network layer, it runs over TLS, but it's not actually defending against active attackers very much in the following sense. This TLS session opens a connection to some server, and as we talked about last time, the TLS connection is going to expect a certificate for some name. But it's not actually clear what name you should be expecting, as we were talking last time. where you want to send an email message is some domain name like, I don't know, IBM.com. IBM.com might have a DNS record that says, my email goes to these 3 servers. That DNS record is not actually authenticated, and those servers don't actually have to be in the IBM.com domain for that matter. As a result, you don't know what is a valid server that you should give your email message to for IBM.com and what are not valid servers for that purpose. So as far as I understand, pretty much every mail server doesn't actually bother checking the name on the certificate for the TLS session that SMTP runs over, because the protocol doesn't actually have a clear answer for what name you should be expecting. This wasn't even a question that SMTP had in mind initially. Okay, so why not require the certificate to be for IBM.com? Well, in fact, because the server accepting your mail is not IBM.com. IBM.com is probably like some very specific machine at IBM, and there's other machines whose job is to accept mail. In fact, IBM might outsource their email to Outlook or Microsoft's cloud service. In that case, the servers for IBM.com could be Outlook.com. They have nothing to do with IBM.com except for the fact that IBM asked them to help. And there's no way this server knows ahead of time what is the mail server for IBM that it should trust versus not. Make sense? Other questions about this sort of story? As usual, feel free to ask questions to Kevin through the online question form. So this is sort of the state of, I guess, one sort of place where encryption does happen in the email world. And I should say IMAP also runs over TLS with similar guarantees. Your mail client might try TLS, might fall back to regular IMAP depending on the email client. But as a result, email does provide some protection against passive attackers. It doesn't provide particularly strong security in the face of active attacks. Another way to think of what email security is about is that the focus of most people working on email security, so to say, has really been on things like spam and phishing attacks. So that's what sort of really gets people's attention with email security. And as a result, the kinds of security mechanisms you see are really targeted at these problems. So there is actually a protocol in email for signing email messages. If you haven't seen it, it's actually kind of cool. It's called DKIM. It's a way, basically, where the sending server signs your message. So in this case of our example email flow, Gmail is actually going to attach an email header that says this message has been signed by, public key of Gmail, and here's the message M. And there's a header that says, yep, Gmail server really sent out this message, and they sign off on it. Now, again, somewhat for compatibility reasons and somewhat because of the immediate motivation being spam control, it's actually your email server attaching the signature, not Alice herself. So you know that maybe Gmail sent this message, which is useful for spam prevention. You don't really know if Alice's client or Alice herself sent this message, which is maybe what you would care for more end-to-end security. Another example of the sort of spam and phishing kind of email defense mechanism is there's another standard called BIMI and VMC, I think, or VMC. This is basically like a sender logo. So the protocol is one where the sending server can actually publish an SVG vector graphic image for what their logo should be. This is great for dealing with phishing attacks because you can associate logos like eBay's logo with ebay.com, and that logo isn't going to show up for a typo eBay with 2 Y's domain.com. So these are the kinds of things that email sort of operators and developers worry a lot about. Spam and phishing, not so much about confidentiality and authentication end-to-end that you might sort of worry about from reading this paper. That makes some sense? So that's sort of the state of email security, if you will. Much more focused on tracking spam, I think, and some per connection, per hop encryption. So how would we do better? So the paper sort of alludes to some kind of an end-to-end encryption scheme. So there's many protocols. We're going to start by describing some very simplistic protocol just to get ourselves something to discuss. So here is a protocol that kind of looks like PGP, which is one of the earliest end-to-end encryption systems out there. So here's a particular scheme. So suppose we have Alice out there that wants to send a message to Bob. And the way our protocol is going to run is that every user has a public key, PKA with SKA over here, and Bob has also a public key of Bob and a secret key of Bob. And let's try to figure out, how do we get Alice to send a message to Bob? So we're going to start by, let's say, sending a ciphertext C, which is going to be an encryption with the public key of the target user and the message we want to send. So that gives us now some sense of confidentiality, because only Bob should now be able to decrypt this message M. So what's going to happen on Bob's side is that he's going to call decrypt, of course, with SKB on the ciphertext C to get back out the message that Bob was supposed to obtain. Make sense? All right, so it gives us some sense of confidentiality. How do we authenticate? Suggestions? Yeah. All right, signing. Yeah, great. Okay, so we'll sign the message. So here's a strawman plan. We will sign with the secret key of Alice. Let's sign the ciphertext that we want to send. That's the thing we sent. We sign it. We sent it. Does this make sense? Is this a good plan? Yeah? I'm sorry? Yeah, so like PGP is a real thing. It's been in existence for like 30 years almost now. I think, yeah, no, it exists. It's relatively not very widely used, I should say. I think there's a lot of difficulties. Basically everything that the paper talks about turns out to be difficult in PGP or GPG. GPG is sort of the modern implementation of the PGP protocol. So one problem with pretty much every messaging system that the paper talks about is key discovery. So how do you get the other person's key? And PGP has basically no answer to this at all. Or it sort of tells the user, well, you go find your buddy's key, and then you can send them email. So that doesn't really lend itself to very good usability. There are some systems that automatically discover keys, but then they're sort of susceptible to attacks where you might discover the wrong key of the attacker, perhaps, instead of the intended user. PGP also doesn't really, well, it doesn't provide some of these properties you might care about, like perhaps some forms of forward secrecy, like we talked about last time. Like if your key is compromised, it would be good if you couldn't decrypt old messages. Well, that's not true with PGP. Might also be nice to have deniability. Like I send you an email message and you get it, you know it's from me, but no one else can, you can't prove this to anyone. It seems like a surprising property. It turns out you can get it, but not with PGP, not with email. So, yeah, PGP is kind of a baseline. You can do it. And, you know, I've used PGP sometimes when I was forced to, but it really takes some effort. There was a super popular study of usability, I think probably like 20 years ago at this point, by some researchers from Berkeley. They actually hired a bunch of, I think, undergrads, like 20 undergrads. They gave them a computer. They said, send a PGP encrypted email message to your buddy. I think pretty much everyone, or maybe all, with the exception of 1 out of 20, they all failed to do so securely. They like either found the key through some insecure mechanism and found the attacker's key, or they didn't encrypt it at all, or they sent it in a way that the other guy couldn't decrypt it. It is just an embarrassing story of usability. And I don't know, I think one way to look at it is it's not like any one of them is a hard, NP hard problem that just like can't solve. Just the whole thing is like a very complicated system, and having encryption that works with everything that you care about, like mailing lists and forwarding and spam filters and all this stuff, that ends up being a difficult thing to do. Sort of empirically, no one's really figured out how to do it, despite cryptography being well understood. Hopefully it gives you some sense of an answer. It's not a sort of a proof that this is a hard problem. Yeah. Mm-hmm. So there are some systems, so there's a question through Kevin about what people do to protect various services that mail out. Like if I get an ad from Amazon or some other, web store, like, oh, here's a sale, please buy some stuff. They typically use some email provider that sends lots of emails on their behalf. There's a lot of protocols out there, adding to this list. There's protocols like SPF, there's DMARC, there's ARC, there's a whole bunch of things. You could Google these things. They're sort of easy protocols to understand if you're curious. And basically, if I want to have some service like Mailgun send email on behalf of my domain, I probably have to get that service registered with all these different protocols so they can send on behalf of my domain without being marked as spam. So there's a bunch of protocols out there that try to address the spam problem. And when you ask when the person anonymously asks how do providers do this securely, in email security means avoid being marked as spam. And these protocols have an answer for how do you avoid being marked as spam, not so much for encryption. Yeah. Other questions? All right. So here's a simple protocol we cooked up. We can encrypt messages, we can sign them. Any thoughts? If this is a secure protocol, are there any things you might worry about here? Yeah. Yeah, okay, so maybe forward secrecy. So we'll get to that in a bit. Yeah? Other things you want to say maybe? Oh yeah, a huge problem indeed, as I alluded to, was how does Alice even know what the public key of Bob is to send? So we'll talk about various, the paper talks about this trust establishment protocols. But one thing I wanted to actually point out is there's super subtle things, even in this protocol, even if you get the key discovery right. So for example, turns out signing the ciphertext is a bad idea. And we should have really signed the plain text of the message that we wanted to send. So here's an attack where here's the way you might look at this and convince yourself maybe this is not quite what you had in mind, which is to say that the person signing the ciphertext didn't necessarily have access to the message. They saw the ciphertext, but they might not be the person that sent the message initially. So it might be the case that there's an attacker, let's call her Eve, over here, and maybe what's going on is that Alice was sending a message to Bob saying, hey, I want to, order this number of items. Here's my credit card number. So maybe the message M is, order foo. Here's my credit card number. So if that's the message, maybe Eve intercepts this message from Alice. She can't decrypt the message. She can't get the credit card number. But what she can do is send the message herself to Bob. And it's going to be the same message, the same ciphertext. She can't decrypt it. She can send the same ciphertext. But she can sign it with her own key, with the secret key of Eve. So now when Bob gets this message, it looks like Eve is sending this message. I want to order, something. Here's my credit card number. Send it to me. And it's signed by Eve. So Bob might charge Alice's credit card number, which is where it came from, and send the goods to Eve. It's not a good protocol. One sort of, rule of thumb for doing security protocols is you should really sign what exactly, the closest thing to what you intended to send. So here, maybe instead of C, what we should be signing is actually signing the message M, not the ciphertext. So signing the message is going to be much better because the person signing the message actually had the message and signed it with their key, so that's the person that intended to send that message. So that seems like a good fix. But even there, we still have a bit of a problem, which is that now we know where the message came from. We have a pretty good binding on Alice sending it to her, to someone, but we don't actually know who Alice sent it to. So here's a weird thing, which is that suppose now we know that the message is something else. Suppose that the message is Alice wants to cancel her order. Cancel my order. So if that's the message she is trying to send to Bob, what she just did is just sign this message with her key. But she didn't actually say in the signature where she was trying to send the message. So now an adversary can take this message and send it to some other site or some other user in the system. So we could take the same message and now send it to, Chuck over here. And it could be that we know the message content, and we know somehow Alice is going to cancel her order. We have a signature from Alice on that message. In order to make Chuck think that Alice sent him this message, all we have to do is produce a new ciphertext. So C prime, we're going to encrypt with the public key of Chuck this same message. So if we guessed right, this will work out. If we know Alice is canceling an order, this will work. And we can attach the same signature, and it'll work. Chuck will think Alice sent him a message to cancel her order. Does this make sense? Sort of the steps of the attack are clear. How would you fix this? Yeah? Any thoughts? Yeah, so where should we specify the recipient? In the encrypted message? Well, could be. So if we stick the recipient in the encrypted message here, maybe we could say, to Bob over here. So if we stick it in the encrypted message, the adversary could stick it here and say to Chuck. No problem. So that's not really going to help. The adversary can still fool us, sticking in the encrypted message. What should we do with it? Well, one thing we can do is actually stick it in the signature. So probably a good idea is in the signed message, we should both say the message, and we should probably say what it is we're signing about the message. It's not like this message is just true in general. It's that Alice wants to send to Bob. So we should probably send both, like who is sending a message to whom, plus the message. That's the thing that we should really be signing. So this is all sort of going to show that even designing sort of low-level details, like fairly simple uses of encryption and signatures, is super fragile and error-prone. That sort of makes this problem particularly hard because, indeed, there's no sort of TLS-like equivalent to save us here. So every messaging system has to get this right again. Anyway, so there's sort of a way to sign a message. We include where you're sending from, where you're sending to, the message itself. This is roughly what PGP does, and this gets you, I think, the kind of confidentiality and authenticity properties that you might intuitively expect from a secure messaging system like this. Does this make sense? Questions? So, tricky enough to get all this stuff right. So let's look at how we might actually address some of these problems that the paper points out. So the paper sort of starts with, various much more sophisticated schemes than this PGP-like strawman I described over here. There's many reasons you might be more sophisticated, but the paper sort of boils down the kinds of problems that you worry about into really three categories that we'll try to talk about here. So one is, as we talked about, this idea of trust establishments. So how do you get the public key of the other person? This is the same problem that certificates was struggling with for us in the context of TLS, but in messaging security, TLS certificates don't really work out as well, at least directly, although the solutions look similar enough. Then there's sort of conversation security. How do we actually encrypt messages themselves once we've gotten the right public key of the other party? And how do we do transport over the network? And this boils down to hiding who you're even talking to. So we'll talk about these three different things and various ideas that the paper sort of sketches out for how you might go about solving them. I should say, like the reason this paper is cool is it talks about gives you a pretty broad survey of all kinds of techniques you could use and even the things to worry about in all these different categories. It's not to say that any one of the schemes that they present is particularly fantastic in their own right. Many of them are used, etc. But I think the really cool thing about this paper is sort of the broad survey. The specific evaluation, they have these giant tables. They're kind of nice and all, but I don't think the specific evaluation criteria are used by anyone else. That's really the survey. That's the cool thing about this paper. It tells you about a whole bunch of ideas that are useful to know in life. Any questions so far? Good. All right. So let's dive into trust establishment. This is the same problem as we were talking about as being sort of roughly certificates. So how do different messaging systems actually deal with trust establishment? The most sort of straightforward plan is maybe positively called opportunistic. So this is basically what SMTP TLS does. Protocol like start TLS there. They basically don't really care who they talk to. They'll talk to anyone. Just ask them what your public key is. You tell them the public key, and they'll encrypt for you. So the reason this works super well is that it's convenient and easy to deploy and compatible. You can add opportunistic encryption to existing protocols fairly easily. But the bummer is that this only works against passive attackers. If there's an active attacker, of course, they can mount a man-in-the-middle attack and give the adversary's public key, and then this doesn't provide as much security as you might have hoped. So another scheme you might consider is what the paper describes trust on first use, or TOFU. This is a sort of you can think of as a variant of this opportunistic scheme. So the idea is that the first time you connect to somebody, or the first time you talk to your friend, you just take whatever key they claim to have. But once you've talked once, you just expect them to have the same key again and again. So one nice thing about TOFU is that it's kind of convenient to use. Maybe this is sort of easy to use again. But one benefit, I guess, is that it actually defends against active attacks to some extent. As long as they're not the first time. So if there's an active attack the first time you talk to your friend, well, the adversary can intercept the communication. But if the attacker tries to interject themselves the second time or third time you talk to your buddy, well, then TOFU is going to save you. Make sense? So what's not so great about TOFU? Yeah? Yeah, okay, so first attempt, of course, is a downside, yeah. Yeah, so that turns out to be a real problem for TOFU, is what do you do with rekeys? So the first time you talk to your buddy, everything is great. You get their public key, you can talk to them, but suppose your buddy upgrades their phone, gets a new device, or loses the old one, installs this messaging scheme again. Now they have a new public-private key pair. Now you get an annoying message on the other end, like your buddy's key has changed, someone is man-in-the-middle attacking them. Probably not the case if your buddy just reinstalled the app, but now the user doesn't really know what to do. It's not really clear what a TOFU user should do if the key mismatches, because the way you got the key in the first place is you just trusted that it was okay. So the user didn't really have any way to decide whether it was good or not the first time, but somehow they now need to decide a second time whether it's good or not. So as a result, TOFU is not super widely used. Sort of an interesting thought experiment, if you will, in the context of messaging systems. It's used by SSH, as we talked about, but it's not super widely used in messaging systems because it actually has really pretty weak usability in this rekey scenario. If your buddy gets a new device, TOFU has a real problem. And sort of the last thing to talk about is out-of-band communication or authentication. So the idea is that you might walk up to your buddy and they show you their public key, maybe as a QR code on their phone, and you scan it with your phone, and this way you actually just literally copy your buddy's public key onto your device. Now you know what the public key of your friend is. So, think QR code here, and QR code from your buddy's phone right when you meet them in person. So the benefit of this out-of-band key exchange is that it is really secure against man-in-the-middle network attackers. So it has strong security guarantees. But the downsides, as you might imagine, well, the sort of one obvious downside is usability, is that it's actually pretty difficult to talk to a friend. Like if I decide, I want to talk to Kevin over this messaging app, I got to find Kevin in person, get his phone out, scan his QR code, all this stuff. That's going to be cumbersome. A sort of more subtle downside of this out-of-band establishment is, again, this rekeying problem. If I meet a buddy of mine and I get their key through a QR code, that's all well and good. I'm talking to them securely. But if they reinstall their phone or get a new phone, now I can't talk to them anymore until I meet them in person again and get their QR code a second time, the new QR code. Again, sort of this out-of-band scheme does get used sometimes. It's an option in many systems like Signal, for example. You can get a QR code out of Signal if you really want, but it's not the default because the usability of that sort of approach is pretty weak. Does this make sense? What's going on? Questions about these different plans? Hopefully makes sense to some extent. So common themes we're seeing here is that convenience is a big deal. And there's really sort of a trade-off in some ways between convenience and some kinds of security here. So we see that out-of-band codes are secure, but really are hard to use, and maybe tofu and opportunistic are the other way around. But another thing to really notice is that recovery, as often is the case, turns out to be the really hard case. The first time you talk to someone, things are maybe easier, but dealing with recovery and differentiating or distinguishing recovery from attacks, that turns out to be really tricky. And you can sort of see it here. Rekeying, that's the recovery step. They don't really have a good answer for what to do. And all the stuff, I guess, yeah, usability, there's a really tension with recovery and security properties. Make sense? Questions? All right. So these are sort of the simplest trust establishment schemes. I wanted to talk about a couple of other ways to do key establishment that's a little bit more sophisticated or widely used. The baseline for a bunch of these things is that we're going to have a server involved. So some kind of a server assisted, some kind of a directory server that's going to help us with trust establishment. So the example the paper brings up, in this case, many systems work like this, but Apple's iMessage is a pretty common example of that. So Apple is going to have a server that kind of like operates like a CA, effectively, a certificate authority, and there's probably going to be a name, a username in Apple's system, and a public key, and we'll have, Alice over here with her public key, and in Apple's iMessage world, you have to have an account with Apple in order to use iMessage. So if Bob comes along and wants to register and start using iMessage, they actually have to log into the server with their password or however they authenticate to the server, and then they're going to send a register operation, very much like you would send to a CA, and say, well, here's my public key, PKB, and Bob has the corresponding secret key. And the server is going to stick it in the table. Bob is PKB. So that's how iMessage or many of these sort of server-assisted schemes work. The nice properties is that it has a nice usability for the reason that you can just start chatting with some user by just entering their username. So if someone tells you, oh yeah, just like iMessage me, my name is Bob, you could ask Apple's server to look it up, or iMessage will automatically ask Apple for Bob's key from this table, and we'll start messaging Bob. You don't need to do any of this QR code business or tofu or anything else. Make sense? Usability is pretty good. Any other thoughts? What's good or bad about this server-assisted scheme? Yeah? Yeah, so one downside is indeed a compromised server is going to be really bad. So Apple is hugely important to the security of iMessage here. So if you break into the server, you can change everyone's keys. Any other thoughts? Yeah. Yeah, so a whole other dimensions. Okay, the question is if Bob has a laptop and a phone and a desktop, what happens? That's a real, actually, tricky problem for these schemes, for end-to-end encryption schemes, because either all these devices have to share the same secret key, and distributing that secret key now becomes a problem. Like I buy a new phone, how do I transfer the secret key from my desktop? That's a sensitive operation. Or the devices have different keys, which is actually kind of good. If you lose a device, you don't lose the big secret key that you had. But now you have a problem synchronizing your state between devices. So in terms of iMessage, I got to admit, I don't actually know what iMessage literally does. I don't actually have an Apple device. I don't think my entry is anywhere in Apple's servers. But you could imagine, I guess, either of these two schemes. I don't know what they actually do. In any case, it's got to be that you would have to authenticate yourself with your password to register a public key. Whether you register multiple entries, one for each device, I'm not quite sure. Perhaps that is how it works. Yeah. Other questions? All right. Another, I guess, thing to worry about in these protocols is that you might think that your security is sort of rooted in these public keys. But in fact, it's not just compromising Apple's server that could corrupt this table. It could also be logging in with Bob's password could corrupt this table. So actually, the password allows changing the key. So if an adversary can guess your password, they can log into Apple, change the public key register for you, and then intercept your messages that way. So, it's end-to-end encryption, but your password plays a huge role now, or your account at Apple. So it's has some caveats, of course, here. Make sense? A final, actually, I guess, positive thing I should say, just to sort of say why this is actually a pretty cool scheme, is that very much like CAs, Apple actually doesn't have the secret keys. So the secret keys stay on the user devices, and even if Apple wants to monitor your communication, it cannot passively monitor your communication because the messages between you and your buddies is encrypted with keys that Apple doesn't have. So in order to mount an attack, Apple would really have to be maliciously supplying bad keys or something along these lines. But it is kind of a nice design in that Apple doesn't have any ability to decrypt your messages unless they sort of quite actively attack you. Make sense? Any questions about this scheme? All right. Another cool scheme I wanted to describe, that's sort of a variant maybe of the server-assisted directory scheme. Or I should say, the reason this might not be the best solution or the reason you might want something more is really this point of a compromised server. And you might worry that either the server is compromised or that the server is just actively malicious. Who knows? That's sort of the weakness, the reason you might look for something more. Had a question? So, okay, the question is this scheme just like MIT client certificates in the browser, you're probably asking? MIT has a public key server that runs a PGP key server, if that's what you're referring to. MIT has a PGP key server where basically anyone can upload a statement saying my PGP key for this email address is this public key. Anyone can upload a key for me, anyone can upload a key for you. And then it's up to you, the user, to figure out if that's the right statement or not. And there's a complicated scheme that PGP envisions called the web of trust, where various users sign other users' keys, and then you weigh, do you trust Bob to sign this key from Alice, and so on. That's not super usable. It's entirely unusable, I would argue, and not super widely used in sort of the broad messaging security community. Some users do use this. No, so Keybase works actually quite differently. So let me tell you what Keybase does. So Keybase is really, I think, going after this problem, but somewhat differently. So Keybase is this company that was kind of a cool startup. It was actually bought out by Zoom, for better or worse. And the person that founded Keybase is actually the guest speaker from Zoom that's going to come in a couple of weeks. But what Keybase does is it augments the central server with pointers to other services. So here's the idea. So I might have an entry in this table for Bob. Here's PK of B. And then there's sort of extra field for other IDs, identities that Bob might have. And the idea is that I might not really know that your name should even be Bob in iMessage. Like, how do I know you're Bob and not Bob5 or Bob22 on iMessage? And the answer to that in Keybase is that you're going to rely on existing accounts that the user has. So it might be the case that I have a Twitter account, or if I were Bob, I might have a Twitter account for Bob22. In that case, I can actually post as Bob22. I can post a message in my Twitter feed saying, Bob22 on Twitter is actually the same as Bob on Keybase. And I can actually sign this message with my secret key as Bob. And Keybase's database is going to have basically a pointer to this message, like a way for the client to fetch this Twitter entry tweet, I guess, from the Twitter servers, from Bob's Twitter account, and saying, if Bob has a GitHub account, then, maybe it's, I don't know, MIT Bob. That's the GitHub account. And similarly, you'll post a message on GitHub under MIT Bob's account, similarly saying, signed with the secret key of Bob, that, GitHub's MIT Bob is the same as Bob on Keybase. And you would update the Keybase server to have a pointer to this entry. So why is this cool? What does this give you that iMessage does not? What this gives you is sort of two things. One is that I don't really have to rely on these names as much. So if I want to find, send a message encrypted to you on Keybase, I could look up, Bob on Keybase, and then it's going to say, well, you're really trying to send a message to Bob. Did you mean this Bob, the Bob22 on Twitter and MIT Bob on GitHub? And then I have to look at these and decide, is that really the Bob I want? So it sort of takes out of the equation who gets to choose these names on the Keybase server. And it doesn't trust the Keybase server as much with keeping these public keys anymore, because I can check that, yeah, it's really Bob22 on Twitter that has the corresponding public key and attests to the fact that, yeah, this really is the right entry on Keybase. The Keybase server is sort of a hint that helps me bootstrap and find all these pointers, but it's not sort of directly trusted. Make sense? So this is what Keybase is doing. That's a pretty cool story. So if you really had to cook up a protocol for key discovery or trust establishment in the terms of this paper, I think Keybase is probably the most sort of sophisticated and credible plan for doing this without central server trust. The nice thing is you can sort of add any accounts you might already have. It doesn't have to be GitHub or Twitter. It could be Facebook or whatever other servers you want. You can all sort of link all your identities to your sort of central key stored in Keybase, and that's effectively going to authenticate you. So there's not even a single server. Like maybe someone compromises the Twitter server, but it's unlikely that someone compromises Twitter and GitHub and all these other identities that you have at the same time. As long as they don't as long as you didn't use the same password everywhere and they can log in everywhere with the same password under your account, then you're probably in good shape. Make sense? So it's probably the fanciest, decentralized trust establishment scheme that people have developed so far. I mean, it's somewhat used. Keybase has some users. It's a little bit inactive now, or like not being actively developed since it was acquired by Zoom, unfortunately. But it does seem like a cool idea. If you wanted to do this, this seems like a good starting point for some next iteration. Questions on what this gives you, etc.? All right. So maybe the last point about how to do trust establishment is that there's a scheme called key transparency that looks quite a bit like certificate transparency that we talked about in the context of certificates, where this is sort of another way to augment a central server to ameliorate the possibility of server compromise. And the idea is that, again, we'll still have this central server that has these mappings, names to public keys, but it's going to publish all the changes to this table into some kind of an append-only log. So this log is going to keep growing. So, maybe when Alice registers, we stick Alice's public key here, and the entry in this log says Alice is now PKA. And then Bob registers with PKB, and then the next entry in the log is going to be, oh yeah, Bob registered, and his key is PKB. And then maybe Bob changed his mind, or some attacker logged in and changed Bob's public key. There's another entry in the log saying Bob has now PKX, I don't know. And now this entry was changed to PKX in the server. So there's sort of a couple of cool things going on here. One is that you have to periodically somehow commit to this log to make sure that it can only grow. So we want to make sure that if Bob registers his key in this log, the attacker can't delete this old entry for Bob's public key. They can only add new entries to maybe modify Bob's key or delete his account or whatever, but it's a log that you can never delete from. And the way this typically happens is you sort of take a hash of the whole log periodically and you publish it somewhere, maybe on some blockchain, maybe in some newspaper, maybe on some website. Doesn't really matter too much. but some way to ensure this log only keeps growing. And then the idea is that everyone is going to look at this log, both the owner of a key and people that want to talk with that owner. So periodically, a user like Bob is going to scan the log and see, oh, well, what are the entries relating to me? So Bob might see that, oh, well, there's an entry registering my key, and oh, here's another entry. Someone modified my key. That wasn't me. Now Bob knows there's a problem, and now Bob can figure out how to tell his buddies that he's under attack. So at least Bob knows someone is impersonating them. And users that want to talk to Bob similarly scan the log and can get a key from the log. Now, in this case, they'll probably send a message to Bob encrypted with this key that the attacker registered for Bob, but Bob will know. So that's the kind of property that you can get with a key transparency design like this, where a user will at least know that they are being impersonated to someone instead of just having no idea that someone's impersonating them to their buddies. Make sense? So this key transparency scheme, I think the paper mentions it a bit. It's still sort of under development. Keybase has a key transparency-like design under the covers, in addition to the Keybase plan I described here. So it's kind of a thing you can add to any scheme, basically. But there's still some hard problems about key transparency, most having to deal with the question of how do you efficiently look up from this giant log. So I sort of drew these arrows where you audit the log or look up Bob's key from this log. But this log could be gigantic, and you don't want to download this whole log of every operation in the world just to find your friend's public key. So coming up with data structures that are both cryptographically authenticated and provide efficient lookup in this giant log, that's a tricky, I think, still open problem, more or less. But, you know, seems like a nice idea. Could be a useful technique eventually. Make sense? All right, so that's key transparency. That's probably the last thing I wanted to say about this trust establishment problem. So just covering public keys is sort of still hard for messaging, just as it was for TLS. And the next thing I want to talk about is a bit of conversation security. So how do we actually deal with conversation security? So one sort of surprise from the paper, perhaps, is how much there is to say about conversation security, aside from just confidentiality and authenticity. I guess one huge group of concerns that the paper brings up is that sort of group chat is hard. And the problem basically comes down to the fact that if you have many users that want to talk to each other instead of just a pair of users, there's a lot of things that you might want to provide, like making sure all the messages are seen by everyone in the same order, or that everyone agrees on who's in the group, or making sure that when you kick someone out of a group, they can't read old messages, that all kinds of properties. We're not going to go into the details here, but it's good to keep this in mind that this is a really hard problem. And as far as I understand, many systems support group chat. None of them really achieve all the properties that this paper lays out, both because they're technically hard and maybe they're not that important. But group chat is a really difficult thing to solve. And many systems don't really provide the strong kind of security guarantees that this paper sort of argues you might want. So that's one sort of maybe thing to learn. Group chat is just tricky to do. There's a number of things that are surprisingly sort of tensions in how do you do your communication security protocol. So one example of a tension is that you actually might want authenticity in your messages. Seems like an obvious thing to want. But you might also want deniability. So deniability is this property that, I could send you a message, but you shouldn't be able to go and tell someone else, oh, Nikolai told me X. You shouldn't be able to sort of, pin me down for having sent that message. You shouldn't be able to sort of construct evidence that I did it. So it's somewhat at odds with authenticity. We'll look at some ways in which you can sort of resolve this tension. That's cool that you can do it at all. But still, there's basically a choice to be made at the top level. Like, do you want a protocol that's going to have a lot of authenticity guarantees, or do you want a protocol that's really much more about deniability and, as a result, sort of short-term conversations where you can't prove long-term where messages come from? So one way to interpret these kinds of trade-offs is that there's not even agreement about what secure messaging means. There's very different kinds of secure messaging schemes that are sort of incompatible with one another. So you shouldn't even expect that there's like the magic messaging system that everyone agrees on. Another tension is you might want confidentiality, fairly obviously. But this is at odds in some ways with spam and harassment. So if your messages are encrypted, it's difficult for servers or recipients in some cases or other parts of the system to check if it's spam messages or sort of annoying messages that you'd rather not have on your platform. This is another tricky problem. Actually, Facebook had this problem to some extent. They have some kind of clever cryptographic construction that lets you encrypt messages, but then if someone reports it as spam, you can decrypt it and prove that someone sent you this harassing message. So it ends up actually affecting the underlying cryptographic constructions to resolve this tension. It doesn't quite fully work out. There's also some tension between the sort of spam and deniability, and so on. These are sort of tricky things to get right. Surprisingly so. You might think, like, how hard is it to just, like, what do you want out of a message? Turns out there's a bunch of things you might want. And we're going to look at a couple examples of how you might actually achieve maybe somewhat surprising security properties in messaging schemes. But any questions before that about what you might want in conversation security or what it even means? All clear? All right. So one thing that I wanted to briefly discuss here is this notion of deniability. It's kind of a surprising thing that you can want or do. And let's look at how, at least intuitively, you might be able to achieve to some degree. So what does deniability actually mean? And I guess I should say, actually, it's not just deniability. Deniability is easy. I'll just send some bits. I never sign or encrypt or authenticate them in any way. If I send them to you, you have no idea if even I sent them. It could be an attacker that sent them. There's perfect deniability there. It's all great. But how do you get deniable authenticity? Like, you have some idea that it's Nikolai that sent you a message, but you can't prove to other people that Nikolai sent you a message. So that's a tricky problem. And sort of, as I was describing, right, the setup is that we have Alice wants to send a message to Bob. It would be great if Alice could, somehow send the message to Bob, and Bob knows that the message came from Alice, but can't prove to anyone that this is the case. This is going to be a surprising construction that you can do because there's a bit of a tension, right? If Bob knows it's from A, why can't Bob convince someone else that this is also the case? So here's the insight. This is going to be fairly a straw man construction, like a very simplistic protocol, but it gives you a sense of how you can do this at all. And here's roughly the construction. We're going to expect our user, of course, to have a public key and a secret key, as always. And the sort of obvious thing you could do that doesn't give you deniability is, of course, like in our protocol there, you could send the message and sign it. Signing gives you authenticity, but now I've sort of committed myself. Bob can take that signature and give it to anyone else and say, hey, look, Alice signed this. That's it. She sent this message. So the way we're going to get around this is that Bob is going to generate a fresh key and send it to Alice, encrypted with Alice's public key. And now, what Alice is going to do is she's going to send this message. We can encrypt it for Bob, but actually here we just care about authenticity and deniability, not secrecy. So we'll just send the message in plain text. And the way we're going to authenticate it is by computing a MAC using this key on the message. So if you remember from the TLS lecture, a MAC is a construction where if you have the key, you can compute the MAC of a particular message. But if you don't have the key, it's just infeasible for you to guess what the value of this MAC would be on a message that hasn't been MAC'd before. So now what does Bob do? Probably you can sort of expect, right? So the thing in the message, we'll call it T for tag. So Bob is going to take the message M and check, is T really equal to the MAC of the key that he generated, and the message he just got? So why should Bob be convinced? I guess there's like two things I want to argue here. One is that this provides authenticity, that Bob knows this message came from Alice. So why is this the case? Well, this is a message for which there is a correctly computed MAC using this fresh key K that Bob just generated. Bob has this key, and the only person in the world other than Bob that has this key is Alice, because Bob sent the key encrypted with Alice's public key. No one other than Alice would have been able to decrypt this key. And as a result, Bob knows that if he got this message, he didn't send any messages himself. Must have been Alice that computed this MAC, or this value T. So Bob is convinced this message is from Alice. That make sense? Why is this deniable? Any thoughts? Yeah. Yes, okay, so you can certainly give some intuition for, there's some deniability thing going on, and in particular, right, like the insight, if you will, is that for deniability, you should encrypt, not sign. This is sort of the opposite of the insight we had for TLS, where for forward secrecy, the insight was sign, don't encrypt. But indeed, so there's something going on, like Alice never signed anything. But how do we argue this is really deniable? Yeah? Okay, so okay, that's a good argument I like about why this is deniable. In particular, you could fake this whole thing on the network as if Alice sent you a message. So here's a story I'll try to cook up for you guys. Like suppose we have Eve, and Eve wants to frame Alice for sending another message, M2. How does Eve do it? Eve is not Alice. She doesn't have the secret key to decrypt the key. But the way Eve is going to try to frame Alice is Eve is just going to generate some new key K prime. Instead of Bob generating, Eve is going to do it. Eve knows K prime. Eve is going to say, oh, well, Alice sent M prime and computed the MAC using K prime on M prime. And by the way, look, we sent K prime to Alice. Or sorry, not M prime, K prime. So Eve can synthesize every single network message in the real protocol as if, or that is indistinguishable from a run of the real protocol. So everything that was sent over the network between the real Alice and Bob can be totally faked by Eve. And this is the sense in which this is a deniable protocol. Nothing that you can derive from the real protocol looks any different from this fake run that we can cook up. So we can fake this whole transcript for any message of our choice. And as a result, no one should be able to generate any, like, if you show someone this tag and this M and this anything over the network, no one's going to be convinced because they can say, oh yeah, I can make up anything you want. Any message M prime, I'll cook it up for you. Does this make sense? It's kind of a cool construction, somewhat subtle. So why is Bob convinced by this protocol run where no one else should be convinced? Well, the reason is that Bob is the one that generated this key. So Bob knows, oh, this is a key that I generated, and I sent it only to Alice. So for Bob, there's a guarantee. For people that didn't generate this key, K prime, they don't really know whether this is real or fake. Make sense? So this is a cool scheme for getting deniable messaging. Now, this literal construction is too simplistic. This was published probably like 25 years ago or something, or maybe closer to 30 now. This is a fairly well-understood property. Many messaging systems actually do provide deniability, like Signal and WhatsApp actually have deniability in their protocol where they don't actually sign with their long-term secrets in quite a way that allows you to get any proof of messages. Although their particular protocol is much more sophisticated than this naive one. Yeah, question?
The question I have is,
Okay, so the question is, what's the value of deniability? People accept screenshots. I think one answer is that, in fact, people are forced to have screenshots, and you might trust screenshots, but it's easy to fake screenshots. So I think it's fairly. I don't think it's this class's job to comment on what people do or do not accept as evidence, but I think it's fairly clear to anyone that screenshots are fakeable. Maybe they'll trust it anyway for whatever reason, but it's very clear. This is something you can fake. On the other hand, some things you cannot fake, like cryptographic signatures. I think then we'd have a very different argument. It's not like someone faked a screenshot. It's like, well, yeah, this was really sent. Maybe someone compromised your computer. I don't know. But this is looking much less like a fake thing. There was actually an example where this was in, I guess, 2016 when Hillary Clinton was one presidential candidate and Donald Trump was the other presidential candidate. There was actually a bunch of emails leaked from Hillary Clinton's email server. And interestingly enough, a bunch of those emails had DKIM signatures on them. And those signatures proved that this leak of email messages was actually authentic messages from Hillary's server. And, probably people would have looked at that dump and said, it seems plausible one way or another. But the presence of DKIM signatures was pretty telling. This is a real, or at least the messages that had the DKIM signatures were real messages. They were really signed. Maybe there were other discussions to be had, but there was not a discussion, is this a fake screenshot or not? It wasn't. Question? Okay, the question is, how does this protocol guarantee to Bob that this message came from Alice? Is that right? So the reason Bob is convinced is because no one else in the world could have constructed this tag with the key that Bob just generated. Well, yeah, because Bob only sent the key encrypted with PKA, and assuming this, Bob already got the right key for PKA for Alice, only Alice will be able to decrypt this message. Eve can force the same message to be logged, right? Here's the thing. If Eve wants to supposedly frame Alice for this, Eve will synthesize all these messages, Eve will send this to Alice, and then it will say, oh, I got this back. Make sense? Question? That's right, yeah. So Eve doesn't need Alice to send this message because Eve picked K prime. And all is needed to compute this is, Eve just makes up whatever message she wants to pretend Alice sent. She can compute the MAC herself on it. And she can pretend like she sent this message to Alice in the first place, as if she was Bob or whatever. Yeah. It's a subtle difference. Takes a while to sink in why this protocol works out, but it's pretty cool. The fancier version that Signal and WhatsApp uses a fancier crypto as well, but achieves the same property where if you're in a conversation with someone over Signal, the messages are coming from the other person, at least authenticated with their public key, but there's no cryptographically signed messages or any cryptographic proof that you can present to another person that would convince them this is really a message from your buddy. Kind of a nice property to have. Yeah. So in this case, I was just looking at the authenticity of a message. So suppose Alice is not really trying to hide that she's saying M. She just wants to make sure that Bob knows it's from her. There's no secret on what M is. She's just not going to say an M that she doesn't like. You could easily add an encryption over here as well. Wouldn't really change it. Yeah. Other questions? Yeah. Did this actually pop up in any legal case? I don't know. And I think having real signed messages like PGP does probably would be a thing that you would just present in a legal argument saying, hey, I got this email. It says so right here. It's signed. You could probably, as we were sort of discussing before, you could probably present screenshots or things like this and present arguments. I mean, even before crypto and computers, you could pick up a piece of paper and say, oh, yeah, here's a letter I got from Bob. He wrote this. And then you could argue, did he or did I fake it or not? And courts are not just crypto. But I think if cryptographic proof was available, I think it would make the argument easier in CRISPR. So I think it's, of course, naive to look at this and say, well, no one will ever know that I sent this. But at the same time, I think it's nice for a messaging protocol to provide this property to make sure that it's not accidentally making it too easy for someone to frame people or to provide proof that this is a message they sent if they don't want to be on record, etc. But you're right. Like, I think it's you shouldn't think that this is like the end story. There's, of course, more to it. Yeah. Other questions? Yeah.
If Eve is trying to frame Alice, would Eve actually send the first message to Alice?
I think it depends. I think all I'm trying to say, I think there's two senses in which Eve is trying to frame Alice. One is that in a sense of, is there anything that Bob can do to prove that this is a real message from Alice? This is an argument for why, no, he can't, because Eve could have synthesized anything that Bob has access to. Could have looked exactly the same. Now, if Eve was a real-world person trying to frame Alice, who knows what she would do, man? Like, that's like beyond the sort of pay grade of this class. Yeah. All right. One sort of interesting thing is that, we talked a little bit about deniability being a plan to like encrypt instead of signing, and forward secrecy, if you remember from TLS, was sort of sign instead of encrypting. Turns out there's a way to get both forward secrecy and deniability. It requires slightly fancier crypto than we're going to dive into here, but it is actually possible. So Signal and WhatsApp have a messaging protocol that gives you both deniability and forward secrecy and some other cool properties that the paper mentions. I guess I should say, in the paper, Signal is called Text Secure. This is the old name of their system. But it's basically the same protocol. So you can get many of these properties together, deniability, forward secrecy, etc. All right, so the last thing I wanted to touch on is the last property that the paper talked about, which is transport privacy. So the problem here is we already talked about how to get public keys across, that's trust establishment. We already talked about how we actually are going to encrypt messages to get deniability, whatever we want, confidentiality, authenticity. Now the question is, how do we actually send these messages across? So this is the problem for transport privacy. So you might have a user A and a user B. They want to communicate. If we literally send a message with maybe encryption, authentication, whatever, doesn't really matter, from A's computer to B's computer, then it may be the case that the bad guy cannot tell what's in the message. Maybe they cannot modify it, all this good stuff. But the bad guy knows that Alice is talking to Bob. That the bad guy knows how many messages are sent, when they were sent, etc. So the bad guy learns a lot about the communication patterns from the transport layer, just the fact that messages are being sent. They're all perfectly well encrypted, but you know what's being sent, or there's something being sent between these two users. So transport privacy is really sort of the paper's way of sort of capturing all the properties you might want of the user to keep this metadata private, to make sure that an adversary can't even tell that A and B are talking to each other. Make sense? As a problem statement? So how do we get some transport privacy here? Well, this is basically a problem for which there's really no great solution, but we'll talk about a couple of schemes. So one thing that you might do instead of sending messages directly from A to B is to go through some kind of a server. You might have A send a message to the server, and the server relays it to B instead of sending it directly. So that helps a little bit. At least the bad guy doesn't see that A and B are directly talking to each other. But this is still not great for two reasons. One problem with this central server is that, of course, the server itself is trusted. So if the server is compromised, maybe the messages are encrypted. So if the messages are encrypted end-to-end, then a compromised server can't decrypt your messages. But the server still will know who is talking to whom. So if you compromise the server, you'll be able to tell that, oh, yeah, A sent a message to B. So the server is going to be fully trusted for this purpose of keeping your transport information private. The other sort of unfortunate thing about this central server design is that it's still susceptible to timing attacks or timing of messages. What I mean by this is that if an adversary cannot compromise the server, the adversary might still be able to monitor the network between the server and the users. So the adversary might monitor the messages coming and going from the server, and the server's job is going to be probably pretty straightforward. If it gets a message in, it's going to immediately send it out to another user if it's just relaying messages. So if I can just monitor the network links on the server, I can see a message came in from A, and then immediately another message went out to B. I can conclude that that's probably A sending a message to B. So with fine-grained timing information, an adversary can pretty accurately deduce who is communicating through this intermediate server, even though they don't have access to the server itself. That make sense? This is a real problem, or, because it depends on what kind of an adversary you're up against and whether you sort of worry about these kinds of transport privacy problems. But apparently, from what I understand, like the government worries about this stuff and they actually monitor timing of messages to infer who is talking to whom if they can't get access to the servers themselves. Like agencies like NSA apparently do this kind of stuff, analysis on messaging systems. One way in which you might get around these kinds of central server designs and get maybe stronger security guarantees is to use multiple servers, I guess is one way to put it. A technique called onion routing. So paper talks about this a little bit, but the rough idea is that instead of having just one server, we're going to have A send a message to a server S1. Server S1 is going to send a message to S2. S2 is going to send a message to S3. And eventually S3 is going to send a message to Bob. So if there's many users using this network, and there's sort of other users sending messages in and getting messages out, then this is maybe more difficult for an adversary to analyze in terms of the timing of messages and provide some degree of security. I guess the most popular version of this that's actually deployed today is Tor, the network that's actually in operation, pretty widely used for anonymously accessing the internet. It's probably about the only credible practical solution to this problem of transport privacy. There's fancier versions of onion routing schemes like these, various kinds of mixed nets, etc. But these things get very expensive very quickly in terms of bandwidth and message overheads and so on. They're really not really practical yet. But Tor is actually deployed. We'll talk much more about Tor. Actually, one of the developers of Tor is coming next Tuesday as a guest lecture. He'll tell you all about Tor. You can ask him questions then. But question in the meantime? Oh, so your question is like about certain attacks on Tor? So very much like we had this central server that had to be trusted. In Tor also, some of these servers better also be trusted. So if an adversary compromised that server for us, we're in trouble in terms of who is talking to whom. Similarly in Tor and these onion routing schemes, if an adversary compromises all these servers, or even most of them, then you're also in trouble. And in this case, for example, if an adversary compromises S1 and S3, then only one server is left in the middle, and then the adversary can mount a timing attack on the middle server very much like they could on just one server. So indeed, there has to be some servers that are not fully compromised here, and the Tor developers worry about this a lot, have all kinds of things to worry about. You had a question? All right, sounds good. Any other questions? Sure, last question. Okay, so your question is to some blockchains like Monero, you're saying, have ways to do perfect transport privacy. It is possible to do perfect transport privacy. The main point is that it's super expensive. One way in which you can get perfect transport privacy is broadcast. If everyone broadcasts their message to everyone else, you have perfect privacy. No one knows who the hell you want to talk to. It's super expensive, though. You send a message to everyone, and you receive a message from everyone. The way you would do the messaging on top of this, of course, on top of the broadcast, is I get a whole lot of messages, and I try to decrypt all of them. Most of them will not decrypt because they're not for me. But the ones that do decrypt, that's a message to me, and I can decrypt and show it to the user. So broadcast gets you perfect transport privacy. Super expensive, maybe I should say, like, way down the list. The worst you can do in terms of performance is broadcast. It will work. And the reason mixednets and Tor exist is that people don't want to do broadcast. It is crazy expensive. Mixednets are only half crazy expensive. Tor is pretty good, not too ridiculous. It's actually in use and people do web browsing through Tor. But we'll talk much more about it next Tuesday. I guess Nick Patterson is going to come by. You should ask him questions then. All right, so that's it about message security. That's a real problem. As I said, one reason it's really interesting is because it's a much wider range of design choices than transport security like TLS, and because there's not a single answer. There's not a TLS of messaging. Every system is subtly different, and we're slowly figuring things out. Maybe we'll get somewhere, but right now it's an open problem in many dimensions, which makes it an interesting thing to poke at. All right, see you guys on Thursday. We'll have a guest lecture by a person from Microsoft who is building their IoT security platform. Should be an interesting guest lecture, hopefully. Come ask him questions.